All right, I'm the last speaker between you guys and happy hour. So I'm going to try to keep this short and sweet and try to keep you entertained. I'm the last speaker of the day. Got lots of interesting stuff to cover. So let's just jump into it. We're going to talk about the role of quantum computing in healthcare. If you have not done much of this before, I'm going to move this down a little bit. We will show you lots of things. And let's see, our clicker's off. Let's try that again. All right, not working.
The Schrodinger's clicker.
It is Schrodinger's clicker. There we go. All right, so noted disclosure, I'm no way representing the official position of Optum or UHG in these forthcoming statements. It's sort of the standard stuff. These are my own opinions and not necessarily representative of the company. So we have to do that. And my clicker is not working. There we go. Optum and UnitedHealth form UnitedHealth Group, the big payer in that payer space. You don't need to know about me. Let's see there. Come on. This is what I want to do. I want to give a quantum computing primer, real quick and dirty, like what is it? And then I want to talk about why we care. Why do you even care? And you should. So we're going to make that argument, right? And then I'm going to develop a context for which you can begin to understand what's happening in the greater industries out there, so you can get past some of the noise that's happening out there. We're going to look at the state of art of quantum computing through the lens of a maturity analysis. Like, how mature is it? And the reason we're going to do that is so you can answer the question, like, when's it coming? It's coming, but when and why and how? And what do I need to look for? What are those markers out there in the industry that give me an indication of it maturing or not? Healthcare use cases. Healthcare is rich. Defense and healthcare, two ends of the spectrum, some of the richest spaces for quantum and AI. And we've been doing this on an educational basis for about 4.5 years. We've got some traction here. We've learned some stuff. That stuff I want to impart upon you. These are kind of lessons learned from our experiences. I want to share them with you too. I think they're valuable. And then if we got some optional examples, I'll show you some examples of some things that can show you elements of quantum. They will be not live today, but I'll walk you through it. So let's just jump into it. Quantum computing primer, right? So the essence of quantum, and this is my only prop of the day, right, is to shred the classical computing of a computational binary bit. Ones and zeros, you can add Boolean logic on that. You can make everything from your cell phone to the spacecraft that sends men to the moon to your Xbox game, right? We want to shred that. We want to take out the classical computing and then do information processing on subatomic particles like photons and neutrons and all that kind of neat stuff that give us access to the quantum world. And so what you have is you move from a qubit that has, that doesn't work, that has ones and zeros. You move from a classical bit that's got ones and zeros to a qubit. Now you still have ones and zeros. Those two balls are at the top, right? But then you have superposition, everything in the middle. And then we call that a magnitude computation. And when you finish all these crazy computations in the middle of the qubit, then you measure it and you can get ones or zeros. On top of that, now in that you have an entire logical construct that you can use for those calculations. But what's not pictured here, we'll show it to you later, is you can also include a second element called phase logic as well. So now you've got two aspects where you can encode data into a single qubit, two separate aspects of computation, both phase computation and magnitude computation. We'll show you that hopefully at the end. And that gives you an idea of how powerful this is. So we'll show you that in an example hopefully at the end. Now, what makes quantum special? Okay, so we're doing information processing on subatomic particles, photons, neutrons, things like that. They're quantum waves. We have to spin those up into superposition because we're working with a qubit. Now that gives us access to all kinds of phenomena that you cannot get in a classical world that we can leverage. Quantum interference is the way we do computation. Take two pebbles, drop them in the ocean or pond or a pool or whatever, you get two waves, right? If the waves are complementary, they're additive, and they get these big swoops, they make each other bigger. Those that are destructive cancel each other out, and you get that flat line across the middle. And all of quantum, the computation that happens in quantum is because of quantum interference. It's not bigger, faster, smaller, cheaper. It's different. And it's like riding a horse and buggy right across a terrestrial plane. That's one way of transportation. Or going through a race car across that same terrestrial plane. That's just bigger, faster, better. Flying a jet fighter across that terrestrial plane, that's different. And that's the kind of magnitude that we're talking about metaphorically. So then you get things like that in quantum entanglement. The best metaphor for quantum entanglement is marriage, right? You're single, you got your own flat, you got your own car, your own identity, your own bank account, right? You get married, you lose all that, right? And then you have a shared account with your significant other. And you can break those things apart and spread them apart light years, hundreds of light years in terms of distance. It's insignificant. What you do one thing happens to another, which drove Einstein batty. But that's one of the part and parcels of quantum capabilities, along with quantum teleportation, that we can leverage to do very interesting things with. These are the promoters. These are the wonderful things about quantum. However, hit the wrong one. Let's try that again. It comes with a cost. There are detractors, right? So that wave function that you need to spin up a qubit in a superposition force so you can do interesting calculations, that's unstable. It's not mature. We'll dig into that a little bit later. Reversible functions. Heat loss occurs in traditional computers. That's why you have heat sinks on your CPU, because you have information loss that causes heat. Heat causes decoherence, and that messes up quantum functions, which are very fragile. There's a no cloning rule. You stick 5 into a variable and you try to copy that variable somewhere else in the classical world. You can't do that in the quantum world. It's not possible. You have a destructive read. You take 5, stick it into a variable A equals 5. You read that once, you get 5. You read it again, you get nothing. Why? Because quantum doesn't allow for multiple reads. You read it once and you're done. The function that spins up that algorithm gets killed and you got to start over again. It's a lot like assembler programming. Anybody do assembler programming here? Right? Did you guys hate it? This is worse than assembler programming. Right? So it's a lot like that, but worse. There's no for loop. There's no abstract programming concepts here. Right? And all this stuff means that there's a horribly restricted problem space. Like, you're not going to walk down to Walmart, throw a quantum computer on your shoulder, go home and play Halo. That's not going to happen. There's only certain types of problems we can solve, and those are either quantum friendly, ones we can force friendly, or ones that we can break apart, get subsets of that, make them friendly, or force those to be friendly. Other than that, at the current state of maturity, that's all we can do. So, why do you care? Why should you care is the next reason. So if you look at history of binary computing relative to that of quantum, you see a history there from vacuum tubes down to solid-state transistors, all the way down to integrated circuits. Okay, that's a history lesson of the maturity of the physical hardware to do that kind of a task. It's 260 years old. It had time to mature. Quantum's only 60, right? We're still in diapers. So things that are trying to mature to become that standard are like superconducting circuits and ion traps and all these other crazy things you haven't heard of before, but it's the same pathway. It's just different. So that's a choke point. This is the key thing that prevents quantum from being on your desk right now, here. And the only reason that's going to get solved is when we take a bunch of physicists and put them to work solving these problems. These are the guys pouring you beers and pouring you coffee at the local barista because they can't get a job until quantum came along, or until a few other things happened in the geopolitical sphere. This is why we care about quantum. And we expect that to be solved. And the reason we expect that to be solved is because there's a massive open, it's not even under the hood, geopolitical conflict right now. And it's not just quantum, it's quantum and AI as well, between two of the world's great superpowers who have means, capability, economic prowess, technical capabilities, governmental support, and academic support, with years of geopolitical decade as table stakes here. And because of that, like the space race, we expect those physicists, as well as a lot of other physicists, to come in and solve these choke point problems that will bring quantum into the mainstream faster than we had previously expected. There's other reasons why as well. Quantum's not a fast follower. You think you can fast follow here, you can't. You got to pay the same tax. You can't get out of grade school and go right into college. You have to go through high school, metaphorically. So there's not a fast forward, it's not a fast follower space. And there's good reason for that. And the other one is global security concerns. RSA, the possibility that RSA encryption might be broken because Shor's algorithm and many others that can do large number factoring. Now, two things on that. The first one is that the NIST, government organization, has come out and chosen a bunch of quantum-resistant algorithms already. That may not make sense to you, but to us it's a flag. It was an indicator to the rest of the industry that you need to get going. That event, when NIST came out, we give the papal blessing to X number of these algorithms, was a sign for the rest of the industries to get going. That was what we were waiting for, and they're in motion now too. Another thing that's interesting here is that there's a recent paper that came out that said if organizations who make the quantum hardware can hit 1,000 qubits of workable qubits, the encryption that is endemic to blockchain, the moment you go out and put something out there, can be reverse engineered and broken theoretically, and we're not that far away. So those things are happening out there, we're starting to see, and this and others as well. But this is an issue of why we are concerned about this. So let's develop some context as I watch my clock. The context I want to develop is for you to be able to look at this industry and get rid of the noise. How do you look at the industry and make sense of this? Like, what are the major moving parts, and what are the stuff you can safely ignore, and what are the things you have to pay attention to? The first one is, if you look at the world in quantum as bifurcated from producers and consumers, it makes a lot more sense. Producers make the tech, like the people who make the phone. Do you care how they make your phone? No, you care what it can do for you. It's the same thing with AI, by the way. Nobody cares what AI is. They just care what it can do for you. And then the consumers, and you're all consumers. There's not a producer in here. There's not a quantum manufacturer in here. Right? You're in that camp. But we need to use that technology to do problems and solve problems of note that are concerning for us. And when you look at the educational needs for that, it's interesting because material science, opaque mathematics, and dense quantum physics are on the producer side. That's where you're hearing much of the hype. Professional consultancy and software engineering are on the consumer side. You don't hear much about that. And the educational component of that reflects that. 99% of everything you pick up is for producers. Only 1% or less are for consumers. That's why we had to roll our own course in that. So producers and consumers. Producers make the tech, consumers use the tech. You've seen the skills already. Other things of note, lots of money go into the producers early on, but then that wanes. It drops like the continental shelf, and it goes right into consumer orientation. Very big returns. And lots of power and things going in there. And there is a maturity concern that we're going to talk about in a little bit. That's a big deal, because I want to show you where we fit on that side. And so to give you reference, a frame of reference, we look back at some of the historical encounters that mimic where this should go, and classical computation is one of those. From the abacus all the way to modern day tablets, right? Something happened, a seminal event happened between 1969 and 73, right? A guy by the name of Dennis Ritchie, who was responsible, by the way, for Steve Jobs, Bill Gates, and Linus Torvalds. So he was the forerunner of all that. He invented the C language and the Unix operating system. Strategically, what that did for us is it allowed computation to move out of these big data centers and into the consumer's hands. That changed everything. When that happened, tons and tons and tons of money flowed into the consumer space and eclipsed the big data center. Anybody been in a big data center lately? Not many, but everybody's got a computer. This has to happen on the quantum side. We just don't know when. We just don't know what the seminal events will happen. And we're going to show you how far off we are from that in a minute. But we do know that that trajectory has to be maintained. So let's embark on a maturity analysis. How mature is the space and why? And what exactly can we point to? Let's try that. Okay. General maturity issues. The material science to hold subatomic particles long enough to do information processing on a high fidelity space and reasonably so is immature. It's being matured, but it's immature. So things that any software engineer would expect to exist don't, like a quantum debugger. Imagine that, right? We don't have one. You got quantum RAM? No, it's on the drawing board. Do you have a quantum IDE at least? No, we don't have any of those. We have no abstract programming concepts, and we have no quantum operating system yet. Now think about how you're going to solve problems without any of those, you software engineers. We don't have those, but they're on the drawing board. But it gives you a sense of maturity. Here's another one. Because you don't have those, the ability to map real-world problems to circuits, quantum circuits on a quantum circuit board, remember I said this is actually worse than doing assembler programming, is uber hard, and very, very few people can do this well. And the people who can don't get let out in public very often. Gives you an idea. And so if you want to get a feel for some of these things, this is one of those problems that you can think about. And if it looks like hieroglyphics to you, it kind of is. You know, this is unraveling the mysteries of the universe to solve a very specific point problem in a quantum way. There's not that many people, I don't care what the rhetoric is, that can do that. And it's people, it's not organizations at this stage. Organizations mean nothing. It's individuals who are brilliant who are doing this. And the idea now is how many of those do you have on staff? And there's not that many. So here we are. Here's a quantum timeline, right? Here's the producer era and the consumer era. And there's some enabling events that allow to make that transition over time. We are way over here on the very left-hand side, right? Just the basics. Producers and consumers are right there. All of these aspects have yet to be developed out there. And that presents a problem for you, because you're a consumer. You can't sit and wait. So we have to prepare for a future that hasn't been invented, and the tools of the trade to do something, anything in that, are still on the drawing board. Okay? The producers are fast inventing those. And the last time I was at a quantum conference, I kind of leaned over and said, hey, you guys, I was in a situation like this. I'm like, can you guys hurry up? I mean, we're sitting here waiting to do work, and you guys haven't invented this stuff yet. But we still have to move forward. You still have to prepare your organizations any way you can to move forward. And you have to do it as inexpensively as you can and useful. So you've got to create POCs. You've got to create educational programs. You've got to create repositories of information. So all that's out there. Now when we take all of that and you look at quantum domains, and there's a lot of them, right? There's healthcare, there's defense, there's transportation, there's logistics, there's all kinds of optimization problems out there. You take a look at the fact that we've got a horribly restricted problem space. It's a lot like assembler programming, only worse. The educational divide is there from producers and consumers, mapping problems in the wild to actual circuit solutions is uber hard. And look at all the stuff that we have yet to invent. That's kind of where we are. That's kind of an absolute assessment for the consumer group out there. And producers, it's different. But consumers, this is where we are. But you still have to move forward. That's the nature of this game. All right, healthcare use cases. So now you know where we're at. You've got a little bit of a primer. Let's look at healthcare use cases. So you get the common use. Oh, I didn't want to do that. Let's try that again. Get the common use cases, right? Drug interactions, genomics, certain types of medicine, protein folding, things like that that are quantum friendly. We know that. But this is kind of a journalistic outside looking in perspective. I want to go the other route. I want to show you what it's like from the inside so you can really see it. So this is what we're going to do. Try it again. There we go. Just like machine learning, right? You take patterns of machine learning algorithms that we know work. They're tried and true. They do certain things, and we map those to problems that seem to fit those. The same thing with quantum. You take problems that we know work, not algorithms that we know work, and map those to problems that seem to fit. We don't take the problem and go find an algorithm because it's not there. But that's the source of innovation. So we can take those known algorithms, map those to problems that seem to fit it, and try to see if it works. And we've got a lot of those in healthcare. We've got a ton, all of those. But I want to run through, before I run through those, I just want to run through one more thing. You can't think of a quantum as a whole computer. It's got to be, think of it as like a GPU with a Q in front of it, a QPU, quantum processing unit. And so when you extricate and break apart problems, you can find subproblems that are either quantum friendly or not. But sometimes we can force them into being quantum friendly, or they're innately problem friendly. And that opens up the aperture to the kind of problems that quantum can solve. And this is the most often used case, where there's a hybrid of what's going on, and you solve one part of it quantumly, and you stitch it back together on the classical side. Given that, it gives us more problems that we can attempt to tackle, like aging, chronic, end-of-life care, patient personalization, precision medicine, electronic medical records, fraud, waste, and abuse, drug development, clinical trials, things like that. Genetics and genomics, we've already got a few patents already in that space, merging quantum in that space as well, and I just went past my slide. Let's try that again. Or not. Internet of Medical Things, operations, the optimization of operations, things like that. Behavioral health is a big deal. So all of these are the types of use cases that we can find fodder for in that space. And, whoops, I'm going back to lessons learned. So let's see how this works. I don't know if I'm doing this.
Yeah.
Are you doing this?
Yeah.
All right, next slide. Next slide. Next slide. Next slide. Next slide. So this is some of the lessons learned. Technical education. So we've been doing this for about 4 years now. We've learned some things. One of those things is that we've taken hand-picked PhDs in our organization, 350,000 people, right? Some of the smartest minds we've ever come across. And we put them in a quantum class that I taught because I developed the course. It's about 6 to 9 months now. And they panicked. Some of these brilliant PhDs, the first 8 weeks, they were beside themselves. We had to talk them off a wall, prevent them from becoming raving alcoholics, all that kind of stuff. They just panicked until about 12 weeks. And then quiescence hit and they started settling down. And that's because, and this is why you can't have fast followers, right? They tried to build a new aspect of knowledge that didn't fit any base that they've built their entire life on, from we to all, grammar school all the way to PhD. And then we put them in a situation that they couldn't use any of that. And they floundered. Like, I haven't had this feeling since grammar school. Like, they didn't know what was going on. Till they started seeing repeating processes and repeating concepts, and then they were able to kind of settle down. Okay? And that's because they were learning everything from scratch. So there's no fast followers in this space. All right, next slide. And then we tried to tell this to executives. That was even harder. Right? So executives aren't going to roll up their sleeves and get their hands dirty, right? They parlay in concepts. And the ability for them to parlay in strong concepts linguistically establishes their ability to run an organization, which means that those things that will be adopted are to a large degree dependent on those things that are understood, that could be understood and that are well understood now, which means those things like around Optum, you can't swing a dead cat without hitting somebody who understands Microsoft SQL. But they didn't understand AI until AI was able to get their linguistic narrative to approach the executives in a way that they could understand, and we shifted it left. Now, quantum is 2 standard deviations around that. That's an area that's not understood at all, and there's no adoption path there. And so our job is to get it to where it's understandable. And that's our problem. That's not their problem, it's ours. And the issue is that the concepts that are indigenous to quantum have no doppelgangers in the clinical world. Try teaching someone something they have no background knowing, and then you're going to be in that space from a conceptual standpoint. And there's nothing even adjacent to it that they can latch onto from the classical world that's very helpful. We have to build all their structures from scratch. Next slide. Other things we learned, that thing is a caveat right there. Like, if you're going to look for problems that are candidate problems to do, either find those that are unsolvable or suboptimally solvable on classical computers. And then if they are in that ilk, then they have to also match to algorithms that we know work. And if that case is true, then you could explore them for possible production. Okay? Unless, and this is the caveat, you're doing it just for the experience, and we're doing just that, right? We have things that we don't need, but we're doing it because the engineering lessons learned from that experience will be hugely beneficial in the forthcoming years. And that's a great reason to do this early on. All right, next slide, please. Quantum is a CapEx cost, is a OpEx cost as opposed to a CapEx cost. You don't have to put a big refrigerator in your basement to do this. You can do this very inexpensively. Actually, you can do it for free on the simulators, and you should do it for free on simulators, and there's good reason you should. And then if you need to go to the cloud, you get guys like AWS and others that have cloud offerings. It's cheap. It's not expensive. You should be playing with this stuff because many people think it's too expensive. It's not. Next slide. So live demos. So what we can do, let's stop there. Then we can open up the floor for 5 minutes, because I see the 5-minute line, 5-minute flag out there for questions, rather than going into demos. Let's ask some questions.